Hello everyone, this is Dr. Hopkins recording the next video in our series. In this video we're going to talk about the Carnot cycle, which is just an example of the second law, or a Carnot engine. What I mean is in any heat engine, we can evaluate it from a thermodynamic standpoint based on the Carnot cycle. So a heat engine, we have a heat reservoir where it's hot. That's going to add heat into an engine. It's going to run based on some kind of fluid. So an example would be steam. The steam engines ran based on this concept. That will do work and propel whatever you're trying to propel or use the engine for. And then any excess heat is dumped into the heat sink, a cold temperature region. Okay. So we're going to have, in this case, we're going to use our working fluid as a gas, okay, because that's what we've been talking about. We've been using gases mostly because we can use equations of state. We're going to alternatively have an expansion and compression of that gas, drawing heat from the heat reservoir, and then dumping heat into the sink. Okay, so let's look at this. So a Carnot cycle, that heat engine, we can evaluate in 4 reversible processes. So because we're doing state functions often, okay, now the work and the heat are not state functions, but the overall internal energy change is, we can represent this as a reversible process. So as long as we don't change where we start and end, reversible and irreversible will give you the same answer for a state function. Okay. So first step, we're going to start at step 1, basically P1, V1 at the hot temperature, and we're going to hold the temperature constant. So it's just going to be in contact with the heat reservoir, and we're going to allow the gas or the working fluid to expand. So that means that we know our work. So it's going to expand and do work on the surroundings. So we're going to get work out of this step. So our work is less than 0, our heat is greater than 0, and then our delta U is the sum of those. Second step, we're going to continue to expand, but now we're going to shut it off from the hot reservoir, and it's going to start dumping to the cold reservoir. So we're going to drop the temperature to the cold temperature. The heat overall is going to be 0 at this point, so it's just the temperature is going to change. The work will once again be less than 0. It's going to do work on this expansion, so it'll do work on the system. And then once we've expanded as far as we can go, we have to reset the engine. So we're going to then do the 2 reverse steps. From 3 to 4 is the isothermal compression, where we're in contact with the sink. All the heat is dumping into the heat sink. And then the work, in this case, we're compressing, so we have to do work on the system. And then the last step is the adiabatic compression back to our original condition, P1, V1, TH. Okay, so you'll notice that this is a complete cyclic process. Okay, so we'll take advantage of that when we do the analysis. And on the top line here, I have the delta U. Of course, since we started at one point, we ended at the same point. That is 0. So that the sum of our heat over the cycle and the work over the cycle is equal to 0. We can add up all the steps. So we had heat in 2 steps. We had work in 4. And then we know that the QH plus QC is going to equal the negative of all of the sum of that work. So we're going to go ahead and from a standpoint of evaluating this engine, kind of play engineer, if you will, and look at the engine efficiency. So how efficient are we at converting heat into work? And here's where this plays into the second law. So our efficiency is the work done divided by the heat withdrawn from the source. Any heat that dumps into the sink is lost, right? Is not used to make work. Okay, and so then we can plug in everything we have here. So we have the work cycle, we have heat, which we can convert to the heat. So we don't need to actually know the work done by the system at all in order to evaluate the efficiency of the system. We just need to know the heat flow from the cold and hot sinks. And you can see we know that, so this is greater than 0, this is less than 0, so this quantity is always going to be negative, so our efficiency is always going to be less than or equal to 1. Statement of the second law, we can convert heat to work but we cannot convert it completely. If we can convert it completely, our efficiency would be 1. Okay, and so the cases where the efficiency of the engine are 1 are where we have 0 heat flow to the heat sink, or we have infinite heat flow from the hot reservoir. So those two cases are a little bit difficult to think about because we're talking about heat. So let's start on, and I'm kind of on the wrong slide here. Let's start on the evaluation of with a known working fluid, say like an ideal gas. So without showing, you can show that this quantity is equal to this. Now I'm not deriving this, although we can. I think it's in your book. And then these are alpha and kappa. Great. Let's put them in terms of our equation of state, so our partial derivatives. And so there is in red is the components that we have, the cold over the hot, and then these two integrals, which are evaluating the isothermal steps, basically. Okay, so let's go in, because those are the ones where the heat flow. And so we have the Carnot cycle. Now let's apply an ideal gas. So if we look at that partial derivative, the partial P over T for an ideal gas is NR over V. So if we plug that in, we're going to go ahead, and I'm skipping the step where I cancel out the NR. So the number of moles in R are constant for this. So then that's just the integral of dV over V, right? Constant temperature, which is just the natural log of these two quantities. So V4, V3 over V2, V1. So our compression and our expansion steps. So remember, this is kind of a reminder of our steps. We're going from P1, V1 to P2, V2. Remember for adiabatic, we did this before. So P2, V2 to the gamma is equal to P3, V3 to the gamma. Remember that was related to our heat capacities and so forth. So we have those 4 steps, and we have those 4 quantities. And we have our temperature and our volume. So let's go in here and look at this. So this is, we plug in for P. This is basically nRTV to the gamma minus 1, right? Because we're subtracting out that 1 right there in the denominator. Okay, so let's go back and actually, sorry, we'll go back to this. And so this NR is going to cancel. We're going to keep the T there, right? Because we canceled the NR up there. So that means that the hot T, so this was the adiabatic step where we had an expansion, the adiabatic compression. We can then make these two equal because they're adiabatic. We know that PV gamma equals PV gamma, and we've added that in. And so then we can rearrange this. So that means the hot temperature over the cold temperature is the same thing as V3 over V2. Or V4 over V1 raised to our quantity there. And then we can rearrange. So this, we don't need this. We can make these two equal, right, V3. And then I have moved the V1 over here, the V3 over here, because remember we're looking at the isothermal steps. And so that means that V1 over V2 to the gamma minus 1 is equal to this quantity to the gamma minus 1. Which means that these two ratios are equal. All right, so let's go back to the expression that we derived for the natural log. So this is the one isothermal step. This is the second isothermal step. We can plug in. So V4 equals V3 is equal to V1, V2. Right, so we have this quantity here. And then if we take the negative of this, we can invert V2 and V1. Okay, because remember, these don't cancel. But now this cancels. We brought the negative sign out here. And we're left with the efficiency of this engine is 1 minus the temperature of the cold over the temperature of the hot. Okay, if we go back and we looked at, and actually, since this quantity is always going to be less than 1, we're always going to be less than 1 in terms of efficiency, which is what we got from thinking about the second law. It's what we got from heat. And so our limit, if we're going to pursue 100% efficiency, our cold sink would now have to be at 0 Kelvin. Now the next step we're going to talk about in this class is the third law of thermodynamics, which tells us that you cannot achieve 0 Kelvin. or it goes to 100% efficiency if we have infinite heat. This is once again something we cannot, or excuse me, infinite temperature. This is once again a temperature that's unattainable. So that means that even based on temperature, not based on heat, the second law restricts the efficiency of our engine. And so basically our maximum efficiency is related in terms of using the ideal gas as a working fluid. The maximum efficiency is related to the two temperatures involved. So we'll do a little bit of work, but this is an example where we can apply our first and second law to a particular system and analyze and show how the second law restricts the ability to convert heat into work. So until next time.